Hello everyone, this is Physics 103. This lesson is on atomic structure. So we will be discussing Bohr's model of the hydrogen atom. So this lesson has two parts. The first part will be talking about the quantization of angular momentum L of an electron using a classical mechanics approach. Okay, so let's introduce first Niels Bohr. So Niels Bohr is a Danish physicist, and he developed an atomic model of the hydrogen atom on 1913. So take note that the Schrödinger equation was developed later on at 1925. So his atomic model of the hydrogen atom uses or is limited to classical mechanics. So he is developing a classical atomic model for the hydrogen atom. So actually there is a lot of classical models developed during that time, but what stood out with Niels Bohr's model in his planetary model was that he introduced some concepts in quantum mechanics. Particularly, he quantized the angular momentum in a classical way. Okay, so we can only quantize angular momentum. We can also quantize angular momentum using the Schrödinger equation, but this was done 8 years before the development of the Schrödinger equation. So he used the idea of de Broglie, wherein de Broglie proposed that matter behaves like waves. So he argued that an electron orbiting around a hydrogen atom or a proton should be treated as an electron wave. So for example, our electron is here. It is orbiting like a wave inside a hydrogen atom with a radius r. So since it is confined in a circular potential, it will exhibit a standing wave-like pattern, such as in this case. Okay, so it will oscillate back and forth in this circular potential. Okay, so let's try to find the wavelength lambda of this electron wave. Okay, so first we know that the circumference of its orbit is always given by, its circular orbit is always given by 2 pi times the radius. And in terms of its standing wave pattern, we know that this can be treated as, from this point to this point, can be treated as one whole wavelength. So using that argument, inside this circle we have two wavelengths. Okay, so if we are to extend or we are to increase the number of wavelengths, we can generalize the relationship of circumference with respect to wavelength to be n times lambda. Okay, so in this case, n equals 2 because there would be two wavelengths associated in this model. In this circumference. Okay, so now we have a relationship n lambda equal to 2 pi times the radius. So we have now expressed lambda in terms of the radius of its orbit. So this is 2 pi r over n. Now, in classical mechanics, we know that the angular momentum of a particle orbiting in a certain potential is given by L equals R times P. Or we say that L equals the radius times mass times velocity, mvr. Now from de Broglie's argument, the momentum of any matter should have a wavelength equal to in this relation. So this is de Broglie's relation. Okay, so also we have defined our wavelength lambda to be 2 pi r over n. So our momentum now in this case will be h over 1 over lambda will become n times 2, sorry, should be the other way around. So this should be n over 2 pi r. I think it's the same. Okay. So now we move r, we multiply this equation by r, and we get p or r times p equal to h over 2 pi times n. So rp equals, recall in our Schrodinger equation we defined h over 2 pi to be h bar. So this is h bar times n. But rp is also the classical angular momentum, L. So now we have a relationship L equals rp equals mvr. So, and we also know that the angular momentum is n times h bar. Okay, so this is the quantized angular momentum. So it is quantized from n equals 1, 2, 3, and so on. So later on, we will see how the orbit of the electron will be quantized from this statement.